In today's video, we're going to look at how to plot polar graphs, so how to graph polar functions. And we're going to use some things called symmetry, zeros, maximum R values to help us do this. And we're going to classify some special polar graphs. But first polar graph we're going to do is we're just going to plot some points. So we're given the equation R is equal to 4 sine theta. So I'm going to figure out if theta is 0, what would R be? R would be 0. And now what if theta was pi over 6? Then we get an R of 2. Now I'm going to repeat these for each of these points. Okay, now that I've found all the some of these major points on the unit circle, I'm going to plot these order pairs, these points onto my polar point. So that's 0, 0. Now square root pi over 6, comma 2 would be about here. Pi over 3 and 3.5 would be approximately here. Pi over 2 and 4. 2 pi over 3 and 3.5. 5 pi over 6, pi over 6 and 2. Oh, I plotted that point wrong. There we go. 5 pi over 6 and 2. Now pi is back to 0. Now, when I do like 7 pi over 6 and negative 2, it ends up being the same point as we have here. So this brute force method of when I just found points on the unit circle and plotted those, these last 4 points are just redundant because it's going over the same points as the ones I've given before. And so this, although I sped up the video, this could be very tedious to do every problem. So this brute force we can do, but you never know how many points to choose. And so we're going to come up with some techniques that can speed up this process. And things that you can look for that helps you sketch the graph faster and help you pick which points to try on your table is symmetry, zeros, and maximum R values. We'll talk about symmetry first. And this is just talking about, these graphs often have a lot of symmetry. There are 3 types of symmetry we see in polar graphs. The first type is in this first diagram, and this is symmetry with respect to the line theta is equal to pi over 2. Or if you're thinking in your Cartesian plane, that's your positive y-axis. And the second graph, symmetry with respect to the polar axis, and the last graph is with the pole. Again, corresponding to our x-y axis, polar axis is the same as the positive x-axis, pole is the same as the origin. Now, there are some ways that we can test looking at the equation if we have symmetry or not. And so if you plug in these values and you get an equivalent equation, then it works. So if we wanted to test for symmetry with respect to the line theta over pi over 2, now notice that if I have this point here, r theta, this opposite point over here has the same radius of r, but it has a reference angle of theta in quadrant 2. Remember how we find that reference angle? That's going to be pi minus theta. So the point r pi minus theta will be on the graph if it's symmetric. Now, what if I did the opposite r? Well, if I did opposite r, that means I need to my graph needs to plot down there in the quadrant 4, and so that means that theta needs to be negative theta. So if you want to test for respect with symmetry with respect to the line theta over pi over 2, it's going to be r is equal to pi, r and comma pi minus theta, or negative r comma negative theta. Now let's look at our polar axis. Here's the point r theta. So to get this point down here, I have the same radius, so it's going to be r, but my angle is now opposite theta, negative theta. So that would work. Now what if I did negative r? Well, negative r needs to end up over here in the quadrant 2, so that would be negative r comma pi minus theta would be our coordinate pair. So anytime you want to test an equation to see if it has symmetry with respect to the polar axis, substitute r with r comma negative theta, and substitute in place of r and theta, negative r or pi minus theta. All right, last one. How do we test and see if it's with respect to the pole? The pole is sort of like the origin on our xy axis. So if I have the point r theta, notice that this point over here has the same, has the opposite r, but the same theta. Or I could have the same radius, and then I'll be in quadrant 3, so the angle would be pi plus theta in quadrant 3. So to test for symmetry with respect to the pole, replace r theta with negative r and theta, or with r and pi plus theta. Now, unfortunately, this test does not always work. Please note that these two tests for symmetry given here are sufficient conditions for symmetry, but they are not necessary conditions. Now, what I mean by that is an equation may fail all three tests, but have one or more of these symmetries, okay? So it can't pass the test and not have the symmetry. So if it passes the test, you're guaranteed to have the symmetry, but it might fail the test and still be symmetric. And the reason for that is because polar coordinates are not unique. As we found before, we can find many representations. So sometimes the test does fail. So we have to rely on other things at occasions. So just do an algebra for this. For right now, we're going to test and see if we have any symmetry with respect to the line theta equals pi over 2 or the polar axis or the pole. So, and also, you can have multiple symmetries. It's not like in the xy axis, if it's symmetric with respect to y, it can't be the x. With polar graphs, you can have more than one symmetry, so you always have to test all three. So I'm going to test with the line theta is equal to pi over 2 using the point r and theta minus pi minus theta. So here I have to do our difference formula for cosine. So it's going to be cosine of pi times cosine of theta plus sine of pi times sine of theta. Now we know cosine of theta is equal to -1, so that gives us negative theta, and sine of theta is equal to 0, so that one cancels out. So I end up with r is equal to 3 minus 2 cosine theta, which is not equivalent to my original expression. So that one, so it's not symmetric with respect to the line pi over 2. So now let's test for the polar axis by replacing every r with r and every theta with negative theta. Now here I have cosine of negative theta. So we need to remember that cosine is an even function. So cosine of negative theta is equal to cosine of theta. So make sure your even and odd functions that we learned earlier in the year comes in very handy. So in this case, we do have the equivalent of the original equation. So we can say that this function is symmetric with respect to the polar axis. Now I'm going to test with respect to the pole. And to test with respect to the pole, I'm going to replace r with negative r, and theta with theta. Plugging that in, I end up that r is equal to -3 minus 2 cosine theta, which is not equivalent to the original function, and so it is not symmetric with respect to the pole according to our algebra test. So the only thing I can conclude from this algebra test is that yes, we have symmetry with respect to the polar axis. All right, so we're going to test replacing r with r and theta with with pi minus theta. So we're going to do our difference formula for sine. So sine of theta times sine of pi times cosine of theta minus cosine of pi sine of theta. Substituting in 0 in place of sine of pi and 1 in place of -1 in place of cosine of pi, we end up with sine theta. And so we get 2 plus 4 sine theta, which is equivalent to our original. And so this is symmetric with respect to the line theta equals pi over 2. Now to test for the polar axis, we're going to replace r with r and theta with negative theta. Sine of negative theta is an odd function, and so that is opposite of sine of theta. So we get r is equal to 2 minus 4 sine of theta, which is not equivalent to the original. And now I'm going to test for the polar axis algebraically. Pole, by replacing r with negative r and theta with theta. So I end up with r is equal to -2 minus 4 sine theta, which is not equivalent to the original, so it fails this test. So our conclusion algebraically that this graph is symmetric with respect to the polar axis. All right, you try this one. Okay, hope you remembered you have to test all three. So we're going to start by testing if it's symmetric with respect to the line theta equals pi over 2 by testing r equals pi minus theta. So I want to replace every r with r and every theta with pi minus 2. So we're going to do, again, the difference cosine difference formula. Simplifying that down, I get r is equal to 3 divided by 2 minus cosine of theta, which is not equivalent to the original, so it fails this test. So now we're going to test with respect to the polar axis by replacing r with r and theta with negative theta. Again, cosine is an even function, so that becomes 2 plus cosine theta, and that is equivalent to the original, and so it is symmetry with respect to the polar axis. I'm not done. I have to also test symmetry with respect to the pole. And I get that r is equal to -3 divided by 2 plus cosine of theta, which is not equivalent to the original. So the only thing I can assume algebraically is that this function is symmetric with respect to the polar axis. Okay, you try this next one. Now notice this time we had a double angle formula because we needed to get down to theta that we can substitute in. So I used my double angle formula, simplified it down. So I have to do my difference formula for sine and my difference formula for cosine. Simplifying this down, I get that the first difference formula is equal to sine of theta. The second difference formula is equal to negative cosine of theta. So I end up with r squared is equal to negative 50 sine theta cosine theta, or negative 25 sine of 2 theta, going back my difference formula. So that is not equivalent to the original, so it fails this test. So now we're going to test and see if it's symmetric with respect to the polar axis by replacing every r with r and theta with negative theta. R squared is equal to negative 25 sine of 2 theta. That should be r squared, not r. And so that did not work out. So now test with respect to the pole, replacing every r with negative r and every theta with theta. I get r squared is equal to 25 sine of 2 theta, so that is symmetric. That is the original, so we can say that this is symmetric with respect to the pole algebraically. Now, these are only tests algebraically. Later on, you could do these tests algebraically. Then, after sketching the graph, you might modify your results to add more symmetry by looking at the graphs, because again, these tests are not 100%. Sometimes they fail when it still has symmetry. Next thing is going to be a tool that helps us graph is finding the maximum R value. This is really easy to do because all of these graphs that we'll be working with mainly, well, we can write every trig function in terms of sine and cosine. So the key comes here that sine and cosine always oscillate between negative 1 and 1. So to find the maximum value, I'm going to replace cosine of theta with 1 or negative 1, depending if I need it, whichever one gives me a positive value. So if I'm multiplying by a negative value, I'm going to replace it with negative 1. If I'm multiplying the trig function by a positive number, I'm going to replace it with 1, like I did in this problem. So we say our maximum value of R is equal to 5. That notation for maximum value is the magnitude of R, or amplitude, but so we can say the magnitude of R is equal to 5, or the amplitude of R. I like to say magnitude of R is equal to 5. So to find the magnitude of R here, I'm just going to replace sine with 1, and I get the magnitude of R is equal to 6, so that's the maximum radius that will be on this graph. So you try the next two. So here our magnitude of R is equal to 1. So our maximum value of R is 1. And our magnitude of R is equal to 5. All right, so next thing is we're going to find the zeros of polar graphs. Finding zero polar graphs are actually pretty easy to do. All you have to do in order to find your zeros is replace R with 0. And then solve the resulting equation for theta and figure out what theta would be. Usually we do this within the unit circles between 0 and 2 pi, but you could do all values as well. So replacing r with 0 and then solving for this, I end up that negative 3/2 is equal cosine of theta. Well, what angles in the unit circle is equal to negative 3/2? None of them, because remember cosine is between negative 1 and 1. So this equation has no zeros. All right, in problem B, I replace r with 0. Solve for theta here. So I end up that sine of theta is equal to negative 1/2. So I ask myself on the unit circle which angle has a sine of theta equal to negative 1/2. And so for positive value, if I'm doing the arc sine again, that's only going to give us values of positive and negative. But putting that onto our unit circle, we're looking at 7 pi over 6 and 11 pi over 6, because those are the two quadrants 3 and 4, that have a sign that is negative from 0 to 2 pi. So now I want you to try, and if I don't ask you for that, sometimes you can give me all the values. So again, it's just going to repeat every time we go around the unit circle. So you can give us sometimes just the points on that. And then the next one. So I end up with 2 theta is equal to 0 plus n pi. And so theta is going to be equal to 0 plus n pi over 2. So if I'm looking at all the angles from 0 to 2 pi that are zeros in this function, I could write that as pi over 2, pi, and 3 pi over 2, or I can just write it as theta is equal to pi over 2n. Now we're going to look at special polar graphs. These are graphs that we should be able to look at the equation and recognize the shape from. And so our first section are lines. If we want to have a horizontal line as a polar graph, it will be in the form of r equals a over sine of theta. Okay, the distance from the pole to the horizontal will always be a distance of a. Vertical lines are r equals a divided by cosine of theta. That'll be a graph of vertical a. And the distance from the pole to the line is a. For a slant line, it's just going to be theta equals some value, a number here, where a is that angle in standard position. Okay, next type is Archimedes spiral. This is pretty cool graph. It's in the form of r equals a theta, where a is any number greater than 0. And you can notice that these have, like, this is the same graph, just went 1 time or 2 times around the inner circle, and you can see how the spiral keeps growing the more you go around the inner circle. Next shape are circles. They can be in the form of r equals a cosine theta, of r equals a sine theta. If it's cosine theta, the diameter will be on the, I guess you could say, equivalent to what you think about as the x-axis. If a is a positive number, it's going to be on that polar axis. If a is a negative number, it's going to be flipped over toward the negative direction. And that distance from the pole to the end of the circle, or the diameter, is going to be your maximum value of r. And it's also going to happen to be the a value in the graph, in the equation. So that is very similar to the same thing that happens for the circle of r equals a cosine. Remember, cosine, think x, negative, so negative x-axis. It's not technically on polar graphs, that's the negative x-axis, but you're so used to thinking x and y on the Cartesian plane, so you can think of it like that. If sine, think sine is your y. So the line, technically on the polar graph, that's the line pi over 2. And again, a is positive, so it's going up, and that diameter is the diameter of a, or that's your maximum r value. If it's sine, it's on the negative y-axis, and it's going down if a is negative. Okay, limacons are our next type of graph, and this is in the form of r equals a plus or minus b sine theta, or a plus or minus b cosine theta. Now, there are 4 different types of limacons. These types of limacons shapes are determined by the ratio of a and b. So if you take those coefficients a and the coefficient b and divide them, and depending on what number you get, and disregard the sign, so you're just looking at the absolute value, you're going to have one of the 4 types of limacons. So the first type is if the ratio a to b is less than 1, and this is called the inner loop limacon. Okay, so the inner loop limacon, as you can see in the graphs below here, has a loop inside the graph, an inner loop. Okay, look at this first graph. Now notice the equation has cosine in it, so think cosine is x, and it's positive between the a and the b. So that means we're going on toward the positive x-axis, or on the polar axis, and that straight line I just drawn is our maximum r value on our graph. Now, if cosine is, if we have cosine and we have a minus in between, we're going toward the negative x-axis. If we have sine and positive, the graph is going up toward the positive y-axis, or the line pi over 2. And if it's sine and negative, I like to think about it as the negative y-axis, or just think it's opposite of the line pi over 2. The next type of limacon that we can have is when the ratio from a to b equals 1. So if a and b are the same number. Okay, this gives us a type of graph that's called, okay, this is also referred to as the heart-shaped graph. As you can see, this kind of looks sort of like hearts that is drawn here. Again, cosine, think x, positive in between, so we're going positive x-axis, and that's our maximum value of r. All right. Cosine, negative between, think of the negative x-axis kind of. Sine is y, positive between, so it's going up on that pi over 2 line. Sine is y, negative, so it's going to the negative pi over 2 line. Okay, the next 2 limacons are called dimpled or convex. Okay, these graphs look very, very similar. They're just a slightly weighted change. You have a slight indentation for dimple, and convex, there's no indentation. So how do you tell? Well, if the ratio from a to b is between 1 and 2, you have a dimple. All of these 4 graphs I'd have here are dimpled. I didn't have enough room to do the graphs of dimples and convex. The only difference between the graphs of the dimple and the graphs of the convex, they are extremely similar. When you graph these, the only difference would be on a convex, you're actually almost doing like a little horizontal line. It's flattened out on that one end where the dimple is on these graphs. So it's just almost completely flat. And these start looking more and more like a circle, just kind of like a circle that's been sitting on the ground and it's gone flat on one side a little bit. Okay, and how you tell if you have a Dimpled, again, the ratio from A to B is between 1 and 2. A convex is if the ratio between A and B is greater than or equal to 2. All right, and then the same thing that's happening up on all these other ones occur. So notice that these are the 4 ratios. We're doing the ratio of A to B, the absolute value, so we're not doing the sign. If it's less than 1, it's an inner loop. Equal to 1, it's heart shape. Between 1 and 2, it's dimple. So as the ratio, and then when it's greater than or equal to 2, it's convex. So as the ratio gets larger, the indentation becomes smaller and more flat until finally we get almost flat with the convex graph. Okay, for a dimple and convex, if you have a cosine, you're going that polar axis and positive. If it's cosine and a negative between, you're going toward the negative polar axis. If it's sine and positive, you're going up toward the line pi over 2. And if it's sine and negative between, you're going down toward the negative pi over 2 line. Okay, the next main group of graphs that we have are what's called rose curves. Rose curves go in the form of r equals a cosine of n theta, or r equals a cosine of n theta. So these are one trig function and you have multiple angles. Now, depending on what the value of n is, tells you how many petals in the roses that are formed. If n is an odd number, then you have the same number of petals as n is. If n is an even number, you have the double number of petals as n is. So for example, on this graph here, n is 3, and then the length of the petal is your maximum value of r. And so I can easily get an equation for this graph by knowing that it's simply r equals 3, which is our maximum, 1, 2, 3, 4, our maximum r value there, sine of 3 theta. Now, on this first graph here, n is, we have a total number of 8 petals. So that means n has to be 4 because it's an even number, and you always double even numbers. Again, I'm going to see how much my radius here. So here my radius is 4 on my maximum radius on the length of the petals. So this equation would be r equals 4 cosine of 4 theta. So these are kind of easy to find. Last type of special graph we're going to look at are limacons. I'm not sure if I'm saying that right, but lemniscates, sometimes I hear it that way. They are in the form, they kind of look like the absolute value, or the infinity symbol is what I kind of think about it. It's in the equation, the form r squared is equal to a squared sine of 2 theta, or r squared equals a squared cosine of 2 theta. Again, shows you the slant of the infinity sign based on if it's sine or cosine. All right, so if you get r squared is equal to a squared cosine of 2 theta, and x, think cosine, think x, and positive, we are just right there on the polar axis, and that distance in between those is a. If it's cosine, you have a negative in front of your squared term. You're now on the you're centered on the line. Theta is equal to pi over 2. For the sine, they're slanted. If it's sine and positive, you're slanted toward sort of like if you think on a coordinate plane system, it would be that line y equals x kind of thing. And if you have sine and you have a negative in front of this square term, think of this as negative y over x for you in your rectangular coordinate system. So slanted in that direction, or that line 3 pi over 4. Okay, so now we're just going to identify which type of graphs these are. So here we have one of our limacons. And so we have to figure out A and B. So A is 2, B is 1. So we're going to do the ratio of A over B. In this case, 2 over 1, and I get 2. So since 2 is greater than or equal to 2, this is a convex limacon. Okay, our next graph is in the form of r equals 2 cosine theta, which is the form of a circle. So this is a circle graph. And it's on the x-axis, so that's circle graph with symmetry with respect to the polar axis, to be exact. Next one is a limacant. Let me say that. Limacant. You try the next two, or next three. Okay, so this one is a plus or minus b sine theta. So this is a limacon, and our ratio is 1. So if it is 1, and it's quadroid, limacon. This one I need to get rid of the parentheses, and oh, it's another limacon. Okay, testing my ratio of a to b. Remember, disregard the signs when you do this because we're doing the absolute value of a and b. We get 3/6, which is 1/2, which is less than 0 or less than 1. So this ratio is a inner loop, limacon. And now we got r equals 4 sine of 3 theta. So we have a multiple angle. So this is a rose curve. And to be exact, it's a rose curve with 3 petals, because we have an odd number that we're multiplying by. All right, so that's how you identify those special. Start memorizing and learning these special polar graphs and be able to recognize them. So you're going to do some memorization of recognizing these special trig graphs and some of the shapes and curves and characteristics of them. And then next class, we're actually going to start graphing some of these functions.